Tubing string, the primary mechanical barrier path. The tubing string forms the main controlled pressure conduit between the reservoir and the surface. During workover operations, once the well is opened and completion components are exposed, the integrity of this tubing becomes one of the most critical elements of the primary well barrier envelope. The tubing string must contain reservoir pressure, transmit mechanical loads, and maintain sealing integrity under variable conditions such as temperature cycles, pressure fluctuations, and fluid changes. A. Tubing body integrity. The tubing body itself must retain its structural and pressure-containing capability throughout production and intervention. This depends on multiple engineering factors. 1. API steel grade. Different grades have different tensile strength, collapse resistance, and corrosion tolerance. J55/N80 low, medium pressure wells. L80 sour service. H2S, good SSC resistance. P110 high pressure gas wells, deep HPHD. Q125/proprietary HPHD grades extreme conditions. Grade selection must account for reservoir pressure, CO2/H2S exposure, temperature cycles, mechanical stress from workover operations, incorrect grade selection tubing collapse, burst, or stress cracking failure. 2. Collapse rating, external versus internal pressure. Collapse rating must exceed the external hydrostatic load, especially during well kill operations. Heavy brines in the annulus. Cooling of the tubing causing pressure differentials. Gas expansion behind tubing. Collapse failure creates an immediate loss of primary barrier and may trap tools or straddle assemblies. 3. Burst rating, internal versus external pressure. Burst resistance must exceed maximum tubing test pressure. Injection pressures. Gas lift injection surges. High rate stimulation, acid, frac, or nitrogen lift. If tubing burst occurs uncontrolled crossflow or direct communication with annulus, violating barrier integrity. 4. Corrosion allowance. Tubing must survive corrosion from H2S sulfide stress cracking, CO2 carbonic acid corrosion, oxygen contamination pitting, produced water salinity, scale deposition promoting underdeposit corrosion. Operators typically apply corrosion allowances, inhibitor programs, corrosion-resistant alloys, CRA. Corrosion thinning equals reduced burst and collapse integrity, primary barrier degradation. 5. Erosion risks. High-velocity flow, especially gas plus sand, can erode tubing ID, creating holes, washouts, ovality, weak spots for future burst failure. Most erosion failures are discovered during workover poo, integrity pressure tests, production logging tools.
B. Connection integrity critical barrier element. Even if the tubing body is strong, the weakest barrier point is often the connection. 1. Premium gas-tight connections. Used in high-pressure or sour gas wells. VAM top, VAM HT, VAM sleegey. Tenorus blue, Tenorus Hydral Wedge series. Hydral CS, Hydral PH6. These connections provide metal-to-metal sealing, high torque capacity, gas-tight performance at high temperature. Workover risk, connection back-off when pulling tubing in stuck conditions. 2. Thread compound and makeup torque. Correct torque equals correct sealing plus structural engagement. Low torque gives leaks. High torque gives galling, thread damage, sealing failure. Torque turn graphs must be verified during tubing running. 3. Seal ring integrity. Premium connections rely on precision metal-to-metal seal rings. Failure modes. Damage from dirty threads, improper handling, over-torque, stress corrosion cracking. A micro-leak at a connection gives loss of primary barrier, annulus pressure buildup, and possible requirement for workover.
C. Tubing hanger seal integrity. One of the most underestimated components in barrier management. 1. Elastomeric seals. Used in moderate pressure wells. Failure modes. Temperature cycling. Chemical attack, aromatics, H2S, CO2. Improper energizing of seals. 2. Metal-to-metal seals. High-pressure, high-temperature wells. High reliability in high-pressure, high-temperature operations, but sensitive to debris. O-ring damage during installation. High axial loads from thermal expansion. A failed metal seal allows communication to A or B annulus secondary barrier activation required. 3. Load shoulder engagement. Tubing hanger must properly land and support axial loads. If not fully engaged, tubing may move. Tubing movement under differential pressure. Seal misalignment. Annulus pressure buildup. This is a major reason for SCP, sustained casing pressure, after workovers. D. Downhole components, each a barrier weak point. Any component installed along the tubing string must maintain integrity under pressure. 1. Gas lift mandrels. Failure modes. Leaking gas lift valve. Mandrel washout. Valve seat erosion. Ruptured check valve. Gas lift leakage, direct communication between tubing and annulus. 2. Sliding sleeves. Used for selective production or injection. Risks. Seal leakage. Erosion at port. Incomplete closure. Debris preventing shutoff. A leaking sliding sleeve equals failed tubing barrier. 3. Nipple profiles. X, R, and no-go nipples. Needed for setting plugs or locks. Failure modes. Eroded nipple ID. Worn sealing bores. Damaged profile preventing plug setting. Seal failure when plug is installed. A plug set in a worn nipple, false barrier confidence. Tubing as a barrier. Complete system overview. This horizontal, full-color technical illustration provides a complete visual overview of how the tubing string functions as a primary well barrier system during workover operations. The layout is divided into 4 major sections, each highlighting a critical element of barrier integrity. 1. Tubing body, left section. A long vertical tubing section is shown with detailed metal wall texture and material grade labels, L80/P110. Icons identify burst resistance, collapse resistance, and corrosion/erosion effects. A red caution box emphasizes, if tubing body fails, barrier lost. 2. Tubing connections, second section. A close-up bubble magnifies a premium connection with metal-to-metal seals and full thread geometry. Potential failure risks such as micro-leaks, improper torque, and thread damage are visually highlighted with red caution indicators. A label notes, connection integrity equals weakest point if not correct. 3. Tubing hanger and seals, center section. A cross-section of the tubing hanger inside the wellhead shows elastomeric seals, metal-to-metal seals, and the load shoulder. Colored arrows represent sealing pressure pathways. A warning states, seal failure, annulus pressure, primary barrier compromised. 4. Downhole components, right section. 3 zoom-in diagrams illustrate a gas lift mandrel, sliding sleeve, and nipple profile. Each shows possible leak paths, seal erosion, and debris-related interference. The section is labeled, any component failure equals loss of tubing barrier. Barrier flow and system message. Green arrows across the top depict normal flow through the tubing. Red arrows at the bottom show how barrier failure leads to activation of secondary barriers such as BOPs, wellhead valves, and lubricators. A final message reinforces the engineering concept. Failure of any tubing element equals loss of primary barrier, increased well control risk.